Imagine stepping into an elevator that takes you not to the top of a skyscraper, but beyond Earth itself, into the deep vastness of space. The concept of a space elevator has captivated scientists, dreamers, and engineers for decades, ever since it was first proposed by Russian scientist Konstantin Tsiolkovsky in 1895, promising a revolutionary way to reach the stars. But how could such a thing actually work? And what engineering feats are necessary to make it a reality? The core idea of a space elevator is to create a tether that stretches from Earth's surface up into geostationary orbit, allowing vehicles to climb directly into space. This would bypass the need for conventional rocket launches, which are costly, require vast amounts of fuel, and come with significant risks such as catastrophic failure during ascent. Instead, a space elevator would provide a more energy-efficient and continuous access route to space, like taking a slow but steady cable car up a mountain, but on an unimaginable scale. Such a system could operate continuously, offering reliable and consistent access to orbit without the high energy demands and costs of traditional rocket launches. To construct a space elevator, the biggest engineering challenge lies in finding a material strong enough to support the weight of the tether while resisting the immense forces acting upon it, including gravity, centrifugal forces, and atmospheric conditions. Carbon nanotubes and graphene are often cited as promising candidates due to their incredible tensile strength and lightweight properties. However, producing these materials at the necessary scale remains a daunting hurdle. Researchers are continuously working on ways to manufacture these advanced materials in large quantities. However, current technological limitations, such as difficulties in scaling up production processes, maintaining material purity, and ensuring consistent quality, make this a long-term goal rather than an immediate solution. Other potential materials, such as boron nitride nanotubes, are also being explored, but they too come with similar production challenges. The tether would need to be anchored to a stable platform on Earth, most likely near the equator, to take advantage of the planet's rotational speed and extend upward to a counterweight in space, beyond geostationary orbit. This counterweight would help balance the forces acting on the system, keeping the tether taut and preventing it from collapsing under its own weight. The elevator cars, or climbers, would ascend the tether using electric or magnetic propulsion, such as linear motors or magnetic levitation systems, carrying cargo and potentially even passengers into orbit. The climbers would need to be powered by a reliable energy source, such as lasers beaming power from the ground, or solar panels capturing energy during their ascent. Despite the significant technical challenges, the benefits of a space elevator are tantalizing. It could drastically reduce the cost of sending materials and people into space, potentially lowering costs from $10,000 per kilogram to just a few $100s, opening up new opportunities for space tourism, scientific research, and even the construction of off-world colonies. Imagine being able to transport supplies and equipment to a lunar or Martian base at a fraction of today's cost, enabling humanity to establish a lasting presence beyond Earth. It could also facilitate the transfer of resources from space back to Earth, such as minerals mined from asteroids, which could have immense economic value. Furthermore, a space elevator could help support space-based solar power stations, which could generate clean energy for Earth, addressing both our space exploration and energy sustainability goals. The environmental impact of space elevators also stands out compared to traditional rocket launches. Rocket launches release significant amounts of carbon dioxide, black carbon, and other pollutants into the atmosphere, contributing to climate change and ozone layer depletion. Specifically, black carbon particles and chlorine-based compounds from rocket exhaust can damage the ozone layer, leading to increased ultraviolet radiation reaching Earth's surface. In contrast, a space elevator would produce far fewer emissions, significantly reducing greenhouse gases and avoiding the release of harmful pollutants, making access to space much more environmentally friendly. A space elevator would have a much lower carbon footprint, potentially making access to space far more sustainable in the long term. Reducing our reliance on chemical rockets would lessen the environmental burden of space exploration by decreasing emissions and minimizing pollutants. While we're still far from realizing this ambitious dream, the pursuit of a space elevator represents humanity's deep desire to reach beyond our planet, to connect Earth with the cosmos in a tangible way. It's a symbol of what's possible when we combine creativity, engineering, ingenuity, and the unyielding spirit of exploration. The space elevator embodies the idea that no challenge is too great if we work together, innovate, and persist in our quest to explore the unknown. As we make strides in material science, robotics, and space technology, the dream of a space elevator may one day become a reality, paving the way for a new era of space exploration that is more accessible, sustainable, and inspiring for future generations. If you enjoyed this deep dive into the possibilities of space elevators, don't forget to like, share, and subscribe for more groundbreaking explorations into the future of space technology.